Chapter Work and Energy. In the previous few chapters, we have discussed or talked about ways of describing the motion of the objects, the cause of motion and gravitation, another concept that helps us understand and interpret many natural phenomena is work. Closely related to the work are the energy and power. In this chapter, we shall study these concepts. All living beings need food. Living beings have to perform several basic activities to survive. We call such activities life processes. The energy for these processes come from food. We need energy for other activities like playing, singing, reading, writing, thinking, jumping, cycling, and running. Activities that are strain us about more energy. Animals too get engaged in activities. For example, they may jump and run. They have to fight, move away from enemies, find food, and find a safe place to live. We engage some animals to lift weights, carry loads, pull carts, and plow fields. All such activities require energy. Think of the missions, list that you come across. What do they need by their working? Why are some engines requiring fuel, petrol, etc.? Why do living beings and machines need energy? Different sources of energy are renewable and also non-renewable. In renewable, you have solar, water, and tides, etc. And in non-renewable, you have coal, petrol, diesel, etc. Work. What is work? There is a difference in the way we use the term work in day-to-day life and the way we use in science. To make this point clear, let us consider a few examples. Not much work in spite of working hard. Kamli is preparing for exams. She spends a lot of time in studies. She reads books, draws diagrams, organizes her thoughts, collects question papers, attends classes, discusses problems with her friends, and performs experiments. She expends a lot of energy on this activities. In common parents, she is hardworking. All this hard work may involve very little work if we go by the scientific definition. You are working hard to push a rock. Let us say the rock does not move despite all the effort. You get completely exhausted, however, you have not done any work on the rock, as there is no displacement of the rock. You stand still for a few moments with a heavy load on your head. You get tired, you have exerted yourself and have spent quite a bit of your energy. You are doing work on the load. The way we understand the term work in science, the work is not done. You climb up the steps of the staircase and reach the second floor of the building just to see the landscape from there. You may even climb up a tall tree if we apply the scientific definition. These activities involve a lot of work. In day-to-day life, we consider any useful physical or mental labor as work. Activities like playing in a field, talking to friends, humming a tune, watching a movie, attending a function, or sometimes not considered to be work. What constitutes work depends on the way you define it. We use and define the term work differently in science. To understand this, let us do the following activities. Activity. We have discussed in the above paragraph a number of activities which we normally consider as work. Think of the situations when the object is not displaced in spite of the force acting on it. Also think of the situations when an object gets displaced in absence of the force acting on it. List all the situations that you can think of each. Discuss with your friends whether work is done in these situations. Work done by a constant force. How is work defined in science? To understand this, we shall consider a case when the force is acting in the direction of displacement. Let a constant force F act on the object. Let the object be displaced through a distance S of the direction of the force. Let W be the work done. We define the work to be equal to product of the force and displacement. Work done is equals to force into displacement, that is W is equals to F into S. In day-to-day life, each of these activities asks the following question and answer them. What is the work done? Work being done. What is happening to the object? What is the work being done? The scientific conception of work. To understand the way we view work and define work from the point of view of science, let us consider some equations. Push a pebble lying on the surface of water. The pebble moves through a distance. You exerted a force on the pebble and the pebble got displaced. In this situation, the work is done. The girl pulls a trolley and the trolley moves through a distance. The girl has exerted a force and it got displaced. So the work is done. Lifting a weight through the height. Here the wrestler is able to move the height from the ground to the upward height of a distance, and then it is called work is done. A closer look at the above situations reveals that two conditions need to be satisfied while calling it a work is done. A force must act on the object and the object must get displaced. If any one of these conditions does not exist, the work is not done. This is the way we view science, work in science. A bullock cart is pulling a cart, the cart moves, there is a force on the cart and the cart is moved, so it is work done. Activity. Think of some situations from your daily life involving work. List them, discuss with your friends whether the work is being done in each situation. Try to reason out your response if the work is done. Which is the force acting on the object? What is the object on which the work is done? Thus, work done by a force acting on the object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. The work has magnitude and no direction. F is equals to 1 Newton and second S is equals to 1 meter, and then the work done will be called as 1 Newton meter. Here the unit of the work is Newton meter or joule. Thus, 1 joule is the amount work done on an object. When a force is 1 Newton displaces it by 1 meter along the line of action of the force. Look at equation 11.1 carefully. What is the work done when the force on the object is 0? What would be the work done when the displacement of the object is 0? Refer to the conditions that are satisfied to say that the work is done. Example, a force of 5 Newton is acting on an object. The object is displaced to 2 meters in the direction of the force. If the force acts on the object all through the displacement, then the work done is 5 Newton into 2 meter, that is equals to 10 Newton meter or 10 joule. Consider a situation in which an object is moving with a uniform velocity along with a particular direction. Now a S F is applied in the opposite direction, that is the angle between the two directions is 180 degree. Let the object stop after a displacement S. In such a situation, the work done by the force is considered negative and denoted in minus sign. It is clear from the above discussion the work done by the force is either positive or negative. To understand this, let us do the following activity. Lift an object up. Work is done by the force exerted by you on the object. The object moves upwards. The force you have exerted in the direction of displacement. However, there is the force of gravity acting on the object. Which one of these forces is doing positive work? Which one is doing negative work? The work is negative when the force acts opposite to the direction of the displacement. The work done is positive when the force is in the direction of the displacement. A porter lifts a luggage 15 kg from the ground and puts it on his head 1.5 meter above the ground. Please calculate the work done by him. The solution is 15 kg into S, that is 1.5, needs to be calculated. Consider another situation in which the force and the displacement are some direction. A baby pulling a toy parallel to the ground as shown in the figure. The baby has exerted the force in the direction of the displacement of the car. In this situation, the work is done to be equal to the product of force and displacement. And then it is considered to be positive. Raised hammer falls on the nail placed on a piece of wood. It drives the nail into the wood. We have also observed children winding a toy when the toy is placed on the ground. If starts moving when a balloon is filled with air and we press it, we notice a change in shape. As long as we press it gently, it comes out to its original shape when the force is withdrawn. However, if we press the balloon hard, it can even explode, producing a blasting sound. In all those examples, the object acquires through different means the capability of doing work. An object having a capability to do work is said to possess energy. The object which does work loses energy and the object on which the work is done gains energy. How does an object with energy do work? An object that possesses energy can exert a force on another object. When this happens, energy is transformed from former to the later. The second object may move as it receives energy and therefore do some work. Thus, the first object had a capacity to do work. This implies that any object that possesses energy can do work. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is therefore the same as that of the work. That is, Joule J, 1 J is the energy required to do 1 joule of work. Sometimes the larger unit of energy is called as 1 kJ equals to 1000 joules or 1 kilojoules. 1 joule is equals to 1 into kg meter squared over second squared. Forms of energy. Luckily, the people we live in provides energy in many different forms. The various forms include mechanical energy, potential energy plus kinetic energy, heat energy, chemical energy, electrical energy, and light energy. Think it over. How do you know that some entity is a form of energy? Discuss with your friends and teachers. Work done, W, is equals to F into S is equals to mg into S. 15 kgs into 10 meter second squared into 1.5 meter. That is equals to 225 kilometer second square. That is equals to 225 Newton meter, or is also called as 225 joules. Let's move to energy. Life is impossible without energy. The demand for energy is ever increasing. Where do we get the energy from? The sun is the biggest natural source of energy. Many of our energy sources are derived from the sun. We can also get the energy from nuclei of atoms and interior of the earth and the tides. Can you think of other sources of energy? Let's move to an activity. A few sources of energy are listed above. There are many other sources of energy. List them. Discuss in small groups how sources of energy are due to sun. Are there sources of energy which are not due to sun? The word energy is very often used in our daily life, but in science, we give it a definite and precise meaning. Let us consider the following examples. When a fast moving cricket ball hits a stationary wicket, the wicket is thrown away. Similarly, an object, when raised to a certain height, gets the capability to do work. You must have seen when the different about different forms of energy. 6 forms of energy, that is, one is kinetic, potential, chemical, nuclear, thermal, and electrical. Here in figure 11.5, the trolley moves towards and hits the wooden block. Fix a stop on the table in such a manner that the trolley stops after hitting the block. The block gets displaced. Note the displacement of the block. This means the work is done and the block on the block by the trolley the block has gained energy. From where does the energy come? Repeat this activity by increasing the mass on the pan, in which case is the displacement more, in which case is the work done more. In this activity, the moving trolley does work and hence it possesses the energy. A moving object can do work. An object moving faster can do more work than an identical object which is moving relative slow. A fast moving bullet, blowing wind, a rotating wheel, speeding stone can do work. How does a bullet pierce the target? How does the wind move the blades on the windsim? Objects in the motion possess energy. We call this energy as kinetic energy. A falling coconut, speeding car, rolling stone, flying aircraft, flowing water, etc. are also possessing the kinetic energy. In short, kinetic energy is the energy possessed by an object due to its motion. The kinetic energy of the object increases with its speed. How much energy is possessed by a body by the virtue of its motion? By definition, we say that the kinetic energy of a body with certain velocity is equal to the work done to make it acquire that velocity. Activity. Take a ball, drop it on thick bed of sand and would be better. Drop the ball on the sand from a height of 25 centimeters and the ball creates depression. And repeat this activity from different heights. You will be finding more depressions and more shallow effects. Compare this with their depths. Which one is the deepest and which one is the shortest. Discuss and analyze, please. Here is the scientist James Prescott Joule was an outstanding British physicist. He is the best known for his research in electricity and thermodynamics. Among other things, he formulated a law for heating effect of the electric current. He also verified experimentally the law of conservation of energy and discovered the value of mechanical equipment of heat. The unit of energy and work called joule is coming after his name. Work and energy. Let us see now how to express the kinetic energy in an equatic form. Let us an object of a mass m moving with a uniform velocity u. Let it now be displaced through a distance s when a constant force F acts on it in the direction of its displacement from the work done. Wf is the work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let b the acceleration produced. In section 8.5, we studied three equations of motion. The relation connecting in the initial velocity u and final velocity v. So v squared minus u squared is 2as. This gives v squared minus u2 equal to s is equals to 2a. From this section, we would know that F is equals to ma. Thus, using the equation, we can work on this. W is equals to m and a. If the object is starting from a station position, that is u is equals to 0, then 12w is equals to mv. It is clear that the work done is equal change in the kinetic energy of a O. If u is equals to 0, the work done will be 2mv. Thus, the kinetic energy possessed by the object of mass m and moving with a velocity v is equals to ke is equals to mv. Another example, what is the work to be done during to increase the velocity of the car from 30 km per hour to 60 km per hour if the mass of the car is 1500 kg. The solution is mass of the car m is 1500 kg, initial velocity of the car 30 km per hour. So 30 into 1000 meters, 60 into 60 seconds is equals to 25 divided by 3 meters second. Similarly, the final velocity of the car is 60, 50 divided by 3. Therefore, we can achieve the car is 12 is equals to mu. 1500 kg into 25 into 3 meters is equals to 156250 divided by 3j. So finally, after working out this, we find the work done as change in kinetic energy is kyf minus k eki, that is equals to 156250 joules. Potential energy. Take a rubber band, hold it in one hand, pull the other. The band stretches, release the band, one of the end. See what happens. It tries to regain the original length. Obviously, the band has acquired energy in a stretched position. How was it to acquire energy when stretched? Take a slinky on shown below. Ask a friend to hold one of its ends. You hold the other end and move away and from the friend. Now you release the spring. Lift an object through at a certain height. The object can do work. It begins to fall when released. This implies that it has acquired some energy If raised to a greater height, it could do more work and hence possess more energy. From where did you get the energy? In above situations, the energy gets stored due to the work done on the object. The energy transferred to an object is stored as a potential energy if it is not used to change in the velocity or the speed of the object. You transfer energy when you search a rubber band. The energy is transferred to the rubber band in its potential energy. You do work while winding the key of a toy car. The energy is transferred to the spring inside and is stored as a potential energy. The potential energy of an object is the energy present in it by the virtue of position or configuration. Take a bamboo stick, make a bow, place an arrow made of light stick on it and with the one end supported by a stretched string. Now stretch the string and release it. You can see the arrow flying from the bow. The potential energy stored in the bow in its used form of kinetic energy in throwing off the arrow and the stretched string. What happened? How did the stringy acquire energy when stretched? Would the stringy acquire energy when compressed? Potential energy of an object increases its energy when raised through the height. This is because work is done against the gravity. While it is being raised, the energy present in the object is gravitational potential. The gravitational potential energy of the object at a point above the ground is defined as the work done and rising it from the ground to the point against gravity. It is easy to arrive at an expression for the gravitational potential energy of the object at a height. Consider an object of mass m. Let it be rise through an height h is from the ground. The force is required to do this. The minimum force required to rise the object is equal to the weight of the object mg. The object gains the energy during the equal to the work done and let us work done on the object against the gravity b. Work done W is equals to force into displacement, that is called as mgh. mp me is energy in joules, m is in mass in kilograms, ag is acceleration of gravity standard 9.8 meters, height is the above the ground. Since work done on the object is equal to mgh and equal to mgh units gained by the object, this is the potential energy of the object. More to know the potential energy of an object at a height depends on the ground level or the zero level you choose. An object in the given position can have a certain potential energy with respect to one level and a different value of the potential energy with respect to another level. It is useful to note that the work done by the gravity depends on the difference in the vertical heights of the initial and final positions of the object and not on the path along which the object is moved. Figure 11.8 shows a case where a block is raised from the position A to B by taking two different paths. Let height AB is equals to h. In both the situation, the work done on the object is mgh. Example, find the energy possessed on the object of a mass 10 kg when it is at a height of 6 meter, given g is 9.8 meter per second squared. Solution is mass of the object 10 kg, displacement height 6 meters, and acceleration is very clear. So finally you get an end result of 588 joules. Are various energy forms interconvertible? Can we convert energy from one form to another? We find in nature a number of instances of conversion of energy from one form or to another. Certain small groups children discuss the various ways of energy conservation in nature. Discuss following questions in your group. How do green plants produce food? Where do they get the energy from? Why do the air move from place to place? How fuels such as coal, petroleum, etc. is formed? What are all the kinds of energy conversions certain to water cycles? Many of the human activities and gadgets we use conversion of energy from one form to another form. Make a list of such activities, identify an activity, gadget, and find kind of energy conversion that takes place. Law of conservation of energy. We have learned that the form of energy can be changed from one form to another. What happens to the total energy of the system during or after the process? When energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to the law, the energy can be converted from one form to another. It can be neither created or destroyed. The total energy before and after the transformation remains the same. The law of conservation of energy is valued in all situations in all kind of transformations. Consider a simple example. Let an object of mass m be made to fall freely from a height. At the start, the potential energy is mgh and kinetic energy is 0. When the kinetic energy is 0, it is because the velocity is 0. The total energy of the object mgh is thus it falls. The potential energy will get converted to kinetic energy if v is the velocity of the object at a given instant. The kinetic energy would become half mv squared. As the fall of the object continues, the potential energy could decrease the kinetic energy, and when the object is about to reach the ground, h is equals to 0, v will be highest. Therefore, kinetic energy would reach the largest and potential energy with the least. However, the sum of the potential energy and the kinetic energy of the object would be the same at all points. That is, potential energy plus kinetic energy is equals to constant or mgh. The sum of kinetic energy and potential energy of an object is the total mechanical energy. We find that during the free fall of an object, a decrease in potential energy at any given point of time appears to be equal to increase in kinetic energy. Therefore, there is also an effect of air resistance on the motion of the object has been ignored. There is thus a continual transformation of gravitational potential energy into kinetic energy. A stronger person may do certain work in a relative less time. A more powerful vehicle would complete a journey faster in a shorter time, and then the less powerful one. We talk of power of machines like motorbikes and motor cars. The speed with which these vehicles can change energy or do is a basis for their classification. Power measures the speed of the work done, that is, how fast or slow work is done. Power is defined as a rate of change of doing work or a rate of change of energy. If agent does a work W in time t, then the horsepower given is as shown 1 HP is equals to 735.5 watts. This is a metric watt. Power is equals to work over time. The unit of power is watt in honor of James Watt. Having the symbol watt is the power of an agent which the work is done at 1 joule per second. We can also say the power is 1 W when the rate of consumption of energy is 1 watt is equals to 1 joule per second. We express larger rates of energy transfer in kilowatts. 1 kilowatt is 1000 watts, etc. The power of the agent may vary with time. This means the agent may be doing work at different rates of different intervals of the time. Therefore, the concept of average power is very useful. We obtain average power by dividing the total energy consumed by the total time. This is another example. Two girls, each of weight 400, climb up a rope through a height 8 meter. We name the girls A and B, and A takes 20 seconds and B takes 50 seconds to accomplish this task. What is the power expended by each girl? So power extended by the girl, so and so, is weight of the girl is equals to mg. The displacement of the height is 8 meter. An object of mass 20 is dropped from an height 4 meters. Fill up the blanks in the following table by computing potential energy and kinetic energy in each of the cases. Height of the potential EP is plus EK, which object energy is located just above the ground. For simplifying the calculations, take the value G as 10 meter second squared. What would have happened if the nature had not allowed the transformation of energy? In this view, the life would not have been possible without transformation of energy. Hope you agree with this. Rate of doing work. Do all of us work at the same rate? Do machines consume or transfer energy at the same rate? Agents that transfer energy to do work at different rates. Please study this activity 11.16. The commercial unit of energy. The unit joule is too small and hence inconvenient to express large quantities of energy. So we start using the bigger unit of energy called kilowatt hour. What is kilowatt hour? Let us say we have a machine that uses 1000 joules of energy every second. If this machine is used continuously for an hour, it will consume 1 kilowatt hour of energy. 1 kilowatt hour is the energy used in 1 hour at the rate of 1000 joules per second. Energy used in the households, industries, and commercial establishments are usually expressed in kilowatt hour. For example, the energy bill comes in the units, which is this unit is called as 1 kilowatt hour. Another activity for you kids. Please observe this meter. Take the readings each at 6:30 AM and 6:30 PM. How many units are consumed during the day? How many units are consumed during the night? Do this activity for about a week. Tabulate the observations. Draw inferences from data. Compare your observations with the details given in the electricity bill. This is another example about finding its power. Weight of the boy is 50 kg. Height of the staircase is 6.75 meters. Time taken to climb is 9 seconds. So P is equals to work done by time taken. That will be finally worked out as 375 watts. Yes. Now let us see what we have learned in the last few minutes. What you learned is summarized in this page. Work done of an object is defined as a magnitude of the force multiplied by the distance moved by the object in the direction of the applied force. The unit of work is joule. 1 joule is equals to 1 Newton meter. Work done on an object by a force would be 0 if the displacement of the object is 0. An object having capability to do work is said to possess energy. Energy is the same unit as work. An object in motion possesses what is known as kinetic energy of the object. An object of mass m moving with an velocity v has a kinetic energy of mv square. The energy possessed by a body due to its change in position or shape is called the potential energy. The gravitational potential energy of an object of a mass m rise through a height h from the Earth's surface is given as mgh, mass into gravitational constant into height. Yes, children. Now there are quite a few exercises available in your textbook. Please go through it, discuss, and try it out all by yourself. These are very interesting exercises. So now we come to the end of the chapter 10 or 11, sorry. Please complete the exercises at home. See you all in the next chapter. Thank you and bye.